Hi guys, so this is the second video on moments. So today we're going to look at non-uniform lamina or non-uniform rod. So let's take this example here. So a mass of non-uniform body can be modeled as acting at its center of mass. So this means the weight of the rod may not necessarily be in the center. Let's take this example of Sam and Tasmin, and we are told that they're sitting on a non-uniform plank AB of mass 25 kg and length 4 meters. The plank is pivoted at M, the midpoint of AB, and the center of the mass is at C, where AC is 1.8 meters. Tasmin has mass 25 kg and sits at A, and Sam has mass 35 kg. How far should Sam sit from A to balance the plank? So first, as usual, we draw a nice big clear diagram and label all the forces. So when you label the forces, we have normal reaction from M, 25G this way, because we're told the Tasmin has mass of 25 kg and she's 1.6 meters away, 1.8 meters away from C. Oh no, sorry. So Tasmin is at A, but the center of the mass of this plank is also 25G, and we put it here. Okay, so the plank is pivoted at M, the midpoint of AB, and the center of the mass is at C, where AC is 1.8 meters. Let's call the distance from M to where the 35G is, because that's the weight of Sam. So we will put a distance x, because we don't know exactly where Sam is for this to be balanced out. So now simply we just take moments, and you'd be wise to take moments about M, so we don't need to deal with this force Rm here. So we have three forces. So if we resolve the first force here, 2 times 25G, and that's 50G anti-clockwise, because if we were to look at the force here, if you carried on, it will carry on going anti-clockwise. And for the next one, we are 0.2 meters away from 25G, so we have 5G again going anti-clockwise. And for the third force, well, we don't know the distance, but we know it's 35G, and the distance we're just calling it x, so x times 35G. So now, because the system is in equilibrium, everything going clockwise is equal to everything going anti-clockwise. So we could simply just equate the two. So we could say 50G plus 5G is equal to 35GX. And then we could group them together and divide both sides by G. And then simply divide 55 by 35. So that will give us the distance 1.57. So Sam should sit 3.57 from A, 0.43 meters from B. Because be careful what the question is saying. Okay, because it says how far should Sam sit from A. So you just simply add 1.57. Okay, so that's how we get 3.57 meters. Okay, so let's look at this example here. We're told the rod AB is 3 meters long and has weight 20 Newton. Notice it's the weight and not the mass, so you don't multiply by G. And we're told it has a horizontal position resting at support at C and D, where AC is 1 meter and AD is 2.5 meter. And this time we're told the magnitude of reaction at C is 3 times the magnitude of reaction at D. It says find the distance of center of mass of the rod from A. So we start off by drawing a nice big clear diagram, and we're going to start putting all the forces in. Okay, so 1 meters from A to C, 1.5 meters from C to D, 0.5 meters from D to B, normal reaction at C, normal reaction at D. Now we're going to estimate where the center of the mass is on the diagram. This time, where do you think it might be? Where would it be closer to? Yeah, so here we're going to estimate the normal reaction at C is 3 times the magnitude of reaction at D. It's going to be closer to here. Because think about it. RC is 3 times RD. So the center of the mass is more likely to be closer to C. Because this value here is 3 times bigger than the value at D. We're told RC is equal to 3 lots of RD. So we could simply replace RC with 3RD because you don't want too many unknown. So now we could just resolve it vertically. So everything going up equal to everything going down. So 3RD plus RD, 4RD is equal to 20. So that means reaction at D is 5. So that means reaction at C must be 15 because reaction at C is 3 times the reaction at D. So now, since we're looking to find the distance, let's take a moment about A because we're asked to find the distance from center of the mass from A. Now you could actually take it from anywhere else and then make the adjustment if you want. But it's just always easier just to read the question and take the moments from where they want you to work in the distance. So these are 3 forces. So why don't you guys pause the video, take moments about A, and see if you could work out the distance from A to the center of the mass. So, first of all, if we take moments about A, we multiply force of 15 Newton with distance of 1 meter. So that's 15 Newton meter anticlockwise. For force 2, we don't know the distance, so we're just going to call it x times 20, and that would go 20 Newton meter clockwise. And for 3, 2.5 meters times 5, and that's going anti-clockwise. Now we know the system's in equilibrium, so if we do clockwise equal to anti-clockwise, and then group them together, and simply divide both sides by 20, that'll give us x equals to 1.38. So the center of the mass is 1.38 meters from A. Alright guys, so here's a past exam question from January 2006 at EXO exam. Why don't you guys pause the video and have a go at this question. Okay, welcome back. So the answer to part A is 1.25 meters. The weight of the mass acts at midpoint. That's the answer to part B. And to C, y is equal to 0.4. Okay, so what we're going to look at now is another question of uniform rod. So here we have uniform rod of length 4 meters and mass 12 kg, and it's resting on a horizontal position as support C and D, where AC and DB are 0.5 meters. So when a particle of mass mkg is placed on the rod at B, the rod is about to point. Rod is on the point of turning about D. So it's very important here for you to understand what it actually means. And we have to find the value of m. So as usual, we're going to draw a nice big clear diagram. Okay, so we label the forces. We got our distance 0.5 meters on either end. Center of mass, because it's uniform rod, 12G would be in the middle. So we know that's going to be 1.5 from C, 1.5 from D. Normal reaction at C, normal reaction at D, and M is placed at B. And make sure you put G because it said the mass of mkg, so it has to be M times G. Okay, so the key word here is the rod is about to turn around point D. So if that's going to happen, then there will be no normal reaction at C. Think about it. If it's going to be turning around D here, okay, so the only way this will happen is if the normal reaction is 0 at the point C. So normal reaction at C will be 0 if it's tilting around D. If it was tilting about C, then the normal reaction at D would be 0, and vice versa. And this is very important. If you don't write that in the exam where the RC is equal to 0, like in this example, and you carry on with the work and you get all the forces and everything labeled correctly, you will get no marks until you write somewhere RC is equal to 0. So now we could start thinking about taking moments about D. So there's a force of force 1, 2, and 3. So why don't you guys pause the video and see if you could work this out. Okay, so this normal reaction at C we said is going to be 0. So the forces that we're looking for are these two forces, 2 and 3. So 1.5 times 12g, so that's 18g, and that is going anti-clockwise. And for force 3, 0.5 times mg, so that's 0.5 mg clockwise. And although it's on the point of turning, the rod is still in equilibrium. So clockwise equals anti-clockwise. And then if we cancel out the g's and multiply by 2, and that will give us the mass of 36. So the mass is 36 kg. And if it's any more than 36, the rod will turn about D. And less than this, less than 36, and then we'll have a normal reaction at point C. Okay, so let's look at another example. So here we're told a non-uniform rod AB of length 10 meters and weight 40 Newton. So notice it's a weight and not mass, so do not include G here. It's suspended from a pair of light cables attached to C and D, where AC is 3 meters and BD is 2 meters. And we're told when a weight of 25 Newton is hanged from point A, the rod is in point of rotation. It says find the distance of center of mass of the rod from point A. So this time it's a similar problem, but it's the other way around. So you've got cable attached. So you're going to have tension at C and a tension at D. So again, we're going to draw a nice big clear diagram. We're going to start labeling all the forces. So we're told AC is 3 meters, BD is 2 meters. So everything in between will be 5 meters because it's a total length of 10 meters. And we're going to estimate the location of center of mass. And we'll put it closer towards C. We've got 25 Newton attached at A. Now, as the rod is on the point of rotating, C will be the pivot, and the tension at D will be 0. So similar to what we said in the previous example. So it's about to tilt at C. So the value here of tension at D would be 0. Since the cable at D is becoming slack, we're going to take moments about, since the cable at D is becoming slack, we'll take moments about point C. So if we take moment about point C, we have these two forces, and the third one, well, the force is 0, so we don't need to worry too much about that one. So if we do 25 times 3, that'll give us 75 Newton meters anti-clockwise. And then for the next one, if we do x times 40, because the distance is x times 40, and that'll give us 40x Newton meters clockwise. And we've already said that TD would equal to 0. Now, same as before, we're going to set clockwise equal to anti-clockwise. So 75 is equal to 40x. So that means x equals to 1.875. Remember, we need the distance from A, so we need to add another 3 on. So the overall distance will be 4.875 meters. So always read the question. It said find the distance of center of mass of the rod from point A.